one with first it's inside the one circle. I gave you a bunch of problems. Do you have any questions about them? Because they're good problems, all of them. Remember, there's three possibilities. You can be inside the one circle, you can be inside the rotated circle, or you can be outside both of them. Yeah, which one, Ben? Say again? 1-4? Alright, so let me first draw a Smith chart. And if you have your Smith charts, I hope you brought a straight edge and some of the Smith charts. Brandon Marcus. Something like that. All right. Can you read it then?
Yeah. It says design an L section matching network matching A minus J50 load to a 50 ohm line.
Then over here we have Z0 50 ohms, right?
Yeah.
Okay.
And then it says determine specific value of long term at a 1 gigahertz operating frequency.
All right, so they give you a frequency at 1 gigahertz. All right, to do this, what's the first step? Anybody? Try it. First, we have to get the normalized impedance. So we find out that Z normalized, Z load normalized, is going to be A minus J50 over 50, right? And that comes out to be what? 1.6 minus J1. Isn't that right, class? Y'all agree with that? All right, now we have to plot it. Where is that located? Well, here's the one circle, right? Our real value is 1.6, so it's inside this circle. Y'all follow me on this? 1.6 would be something like this. That would be the real part of 1.6. Minus J1, well, here's minus J, so it would be probably about here would be ZL. Do you all agree with that, class? Approximately. Do you have your Smith charts with you? If you do, please confirm what I said. Make sure it's about right. You all agree with that? Can you all see it? Everybody okay? You guys got it? All right, now what's the next step? We're inside the one circle, right? No matter what we add in series with this, I can only move along that round trajectory that's inside there. I can never add a series element that will get rid of the reactance and put me on that one circle. Our goal is to be either here or here, and ultimately get back to here. So that means I have to go to the Y domain. You all follow the logic behind this. Everybody? So how do I do that? I take 1 over this, right? And this is not very drawn well, but it should go something like this. And this value, YL, is 1 over ZL. Can you give me that? Anyone?
0.44 plus J 0.28.
44 plus J what?
0.28.
0.28. Now, did everybody follow me why I did what I did? Now, here, listen. Now, our goal is to get to either this part or this part. We were in impedance. This is admittance, all right? If you add a capacitor in parallel, you're moving this way. If you add an inductor in parallel, you're moving this way. Do y'all follow me on that? All right, now, here's where you're going to have to help me. The real part of this is 0.44. So if you go along the trajectory of 0.44, you're going to hit that rotated circle, and it's going to be, I don't know, I need the real and imaginary value of that where it intersects the circle, where the 0.44, the real part, intersects that circle, the rotated circle. Go ahead. All right, I want to make sure everybody understands what we're doing here. Here's our Y value, right? We want to add a component to either moving along the real trajectory. We can change this and get rid of it. All right, we can either add or subtract things to change that value, but we can't change this value. So we're moving along this trajectory, the circle 0.44. So where does this intersect? Here and here. It'll be the conjugate point. Say again? Okay, so it's 0.44, 0.44 plus J what? 0.5 is it? 0.5. 0.5? Is that right, Constance? All right. Now, how far did we have to move? we were at 0.44 plus J 0.25. Is it 0.25 or 2.8? 0.25? 2.8, sorry. Alright, so now I have to get to this point. So if I take 0.5 minus 0.28, right? That's what? 0.22J that I add, and it would be in parallel, so I'll just draw it over here. Here's my load over here. Now I'm going to add a value of plus J 0.22. I'm just going to leave it there so you can understand what I'm doing. Now at that point, I'm right here. Right? So this is 0.1. This is not drawn very well. I'll try to draw it a little better. That's 2. This would be 0.3 right there. Y'all follow me? Class, you all with me? Can you see it back there? I mean, you can shut that door a little. Alright. So now we're here. Now, take 1 over that. And the real value better be about 1. Take 1 over this value of 0.44 plus J 0.5. It's going to come down here to the rim here.
1 minus J 1.1.
1 minus J 1.1. You all follow me on that? We were in impedance. We went to admittance, so we put something in parallel. Now we're back in impedance, right? So I need to add something to this to get rid of that J, or that minus J 1.1. What am I going to add? A plus J 1.1 in series. You all hear me now? Series this time. So this is going to be a J 0 or 1.1, pardon me, 1.1. And this is what it would look like in terms of normalized values of impedance and admittance that I'm adding. Now at that point, when I add that value, then I just have an input of 1, right? Well, if it's 1, that means the input impedance is what? 1 times, that would be the normalized input impedance, 1 times Z naught is Z naught. Now my input impedance is the characteristic impedance of the line, no reflections. That's the goal of this matching. You all with me, everyone? Some of this stuff, if there's little parts you don't understand, you mess everything up. You got to understand the reason we're doing everything. The goal is to have it impedance matched. The goal is to finally just have 1 be the result of adding the elements. That's the goal, because then it's normalized. Everybody with me? And that means when I do that, now I'm right here with reflection coefficient is 0. Okay, now those are the elements. Those are the values in terms of admittance and impedance. Now we need to get the element values. You all with me? So I'm going to start with this one in parallel. That's a capacitor for sure. And the way I do this is, first I think of capacitance in general, capacitive reactance. It's 1 over J omega C. This is the way I do it. You all agree with that? That's the reactance of a capacitor. Normalization means dividing by the characteristic impedance of the line. So then just divide it by Z naught. Now that's the normalized impedance of a capacitor. Admittance is 1 over that. You all follow me on this? The reasoning is critical. Alright, so you'll never get lost if you follow the thought process here. So this is going to be J omega C times Z naught has to be equal to this parallel value, which is J 0.22. And now, we have the characteristic impedance. We have omega, it's 2 pi times 1 gigahertz, right? Now we can get C. You all see how the J's don't matter now, you can cancel. So that means C, and help me out with this one, is 0.22 divided by omega, which is 2 pi times 10 to the 9th, because it's 1 gigahertz, times Z naught, and Z naught is 50, if I don't miss my guess. So what is the value of C? How many have Smith charts here? The rotated Smith charts. Does anybody need any? Because, if you do, hopefully we can. You need some? Can somebody share one with them? Anybody got a spare one? You need one too? There's about 3 or 4 people that need them. Does anybody have some spares? I'll make it right with you. You come up to my office, I'll give you a stack of them. Yeah, make sure you get them. He needs one too. Anybody else? You're going broke on this. It's coming your way. All right. Please just understand, I'm trying to do this, the best way I know how to do this is just do problems on the board like I'm doing. If I do it the overhead, just start doing it loses people. There's little things they don't see. Find out exactly where these points are on that Smith chart, please. And what is this value again, Ben? 0.7 pico? 0.7 picofarads. That is a small capacitor. All right. Now for the next part, it's a series element, right? Y'all hear me? A series element. So how do I find out what this is? I know that's a capacitor, and that's the value. I'm going to draw the final circuit. Well, I know what? If I have a series plus J impedance, it means it's an inductor. Inductors are J omega L, right? So just following on here. So this J1.1 would be J omega L, right? But it's normalized, divided by Z naught, is equal to this, J1.1. Now, you can see, just from that, if you understand the rational thought here, it's pretty straightforward how to get every single value. That means L for that one is what? Well, it would be 1.1 times Z naught over omega. Do you all agree with that? So it's 1.1, right? And then it's times Z naught over omega, which is 2 pi times 10 to the 9. Now Z naught is 50. Can you tell me what that is? There's usually little things that people don't understand that cause big, big problems.
55 nano.
55 nano? Anybody confirm that? All right. Now, I will ask you on Friday to draw the circuit. Hear me on that? I will ask you on Friday to draw a circuit. So when you draw it, don't put the capacitor where the inductor is or the inductor where the capacitor is. Y'all hear me? And the golden rule of thumb is capacitors in parallel, inductors in series. Yes?
Did you go there? Why did you add, how did you add an inductor at 1.1?
Well, this is a series element, right? Let's go back a step. And don't worry, there are no dumb questions. Some of this stuff,
I also didn't divide by 2 pi, it's 8.75.
sorry. 8.75?
Yeah.
That's a small inductor, I want to tell you that. That's a small capacitor, a small inductor. Those are things you probably, if you ever have to deal with things that small, they have adjustable, they're called potentiometer kind of things for inductors and capacitors. It's basically tuning them so you get the exact value you need. Because when you're talking about stuff that is that small, the lead length, just a little too long, especially at microwave frequencies, can change everything. So remember that. Try to, if you ever have to do this for a project, in the real world, especially in your prototyping, make sure you have some measure of adjustability. Have you all seen these capacitor plates that are just air plates? They're like for tuning, that they'll come, you can tune them in and out. Usually if you get a capacitor, you can get the trim pot, something like that you put, so you can adjust it a little bit, because it can drive you nuts if you don't have that capacity. All right, now you were asking about how did I know this is an inductor? All right, first let me go over it. I started by saying no matter what I add in series, I can't get to the outer ring here, the one, right? So I have to go to the admittance domain. Now I'm in the admittance domain, and I want to make sure you see every bit of it. In the admittance domain, the capacitive, normalized capacitive admittance would be J omega C Z naught. Right? Take the normalized capacitive reactance, take 1 over it. You all follow me? If I need to go here, I'm adding plus J. If I need to go here, it'd be minus J. That'd be an inductor. You all follow me? Now this is the parallel element. Now, here's what Ben's asking. I'm here, I put that element in parallel, and now I view everything as an impedance. So I jump back over to the conjugate point. Anytime you go 1 over that point, you go from admittance to impedance or impedance to admittance. You all with me? So now I'm here. That value is J, or is 1 minus J 1.1. I need to add something to get rid of that minus J 1.1. That is a plus J 1.1 impedance. The only impedance is plus J 1.1 is going to be an inductor. An inductor has an impedance of J omega L. Everybody's familiar with this, right? J omega L, positive J. Then I have to divide by Z naught to normalize it. So that's what I did right there. I took 1.1 times Z naught, look at the formula, and then I divided by 2 pi F, the frequency. And you should get 8.75 if that's done right. Everybody confirm that? Y'all follow the thoughts on this one, right? Let me ask you this, and just work with me here, tell me what to do. Even though this is a lousy design, don't do this. But what, if for whatever reason, your boss wants to destroy a circuit for something. If I come here, but I wanna go this way, what do I do? Let's do the opposite problem. Let's start here. All right, that's, gotta get from here to here. Now we're gonna add something here, that will be an inductor, and then we're gonna go to the conjugate point, and it will be 1 plus J 1.1, so now we're gonna add a capacitance here just to get rid of it, then we're gonna go back here. Y'all follow me? Let's do that problem so you can see how to make a bad design. And what some people do, and I know nobody here would do this, they'll take that clip and they'll just have me say, let's make a bad design on YouTube. And I'll get all sorts of heck. I have not had anybody recently do something like that, but long ago, there was really comical students that used to enjoy doing stuff like that. Because anytime that you got a video of Zoom and stuff, you open yourself up. I mean, you can get creamed with some Zoom. Okay, now we're gonna do the opposite problem, the bad design. So, I'm here, everybody just listen. This point right here was 0.44, 0.44 plus J 0.25. Y'all follow me? 2.8. Or 2.8, my gosh, I'm so sorry. 2.8. Everybody with me? Now, listen. This point we know is this, right? If you keep on following that trajectory down here to the opposite point in that rotated circle, this is going to be 0.44. It will be minus, 0.44 minus J 0.28. Can everybody locate that? Can you all find it? Just follow the trajectory, the 0.44 over to this point, right? With me?
Why is it
Minus J 0.28, because this is what minus J's, these are all minus J's, these are all plus J's, right?
So it's supposed to be in the constant admittance. Sorry,
Should that
is
be
that supposed to, like, you have it, it's not
0.4?
exactly your, which one is it?
What's, this is minus J, right? Isn't this point right here, isn't this point, sorry, my bad. I am so sorry, it's minus J 0.5. I am so sorry about that. All right, thank you for correcting me. I gotta stop and look a little more carefully at this. This is the actual point in that circle. This is the conjugate point. All right, can you all find that? I apologize. All right, now that means, how far did I move? I started at J 0.28, right? And I'm at minus J 0.5. So that's a total amount of what? This 0.28 plus 0.5, or I moved minus J 0.78, right? Y'all with me on this? Because that's how much I have to add. So now I'm going to say, and I'm doing this in parallel, it's an inductor, but I'm just going to put down what it is. It's going to be minus J 0.78. Now here's my load. Don't worry about that right now. Now, when I add that on at this point, right? When I take 1 over this, remember that's admittance, correct? 1 over that, I'm an impedance, and I should have 1 plus J 1.1. Just let's see where that is. So if I have an impedance, now that's an impedance of J 1.1. With me on this? Started at impedance, went to admittance, now I'm back in impedance. When I look at this, what do I need to add to get rid of it? A minus J 1.1 impedance. Do y'all follow? All right? So that means I have to add a minus J 1.1. Now we talk about the elements of a bad design. Okay, so think about what I did. First, let's get this one. You all with me? That's going to be an inductor. First, inductive reactance is what? J omega L. You all agree with that? That's the impedance, or I call it inductive reactance. Normalization means divide by Z naught. So now I divide this by Z naught. Now that is what? That is a normalized impedance of an inductor. For the normalized admittance, 1 over that. When I take 1 over that, what do I get? I get minus J Z naught over omega L, right? And what's that equal to? Minus J 0.78. Do you all follow me on this, class? How many do? I'm making sure, I'm trying to be as clear as I can, I'm not trying to do anything here too fast. So that means this is gonna be minus J 0.78. That means what happens? If I want the inductance, what happens? Can you all see it? What do? I take Z naught, right? And I divide it by omega and divide it by 0.78, and I'm going to get my value of alpha. I hope you can see that. You all with me, class? So what's that value going to be? When I take 50 over 2 pi times 10 to the 9 divided by 0.78. Anyone? Sorry, I'm looking for help here. These are not things I can do in my head. Z naught's 50, so this is 50 over 2 pi times 10 to the 9 times 0.78. And what do you get for that? 10.2 nanohenries. Now that's in parallel. Do you all agree?
Yeah.
Okay, next part. We get this. Alright, that is an impedance, normalized impedance, right? The normalized capacitive impedance is 1 over J, or sorry, the capacitive impedance is 1 over J omega C or minus J over omega C, right? To normalize it, I have to divide by Z naught. You all agree with that? So I can say this, minus J 1.1 will be equal to minus J, the impedance is divided by omega C, and then to normalize by Z naught. Correct, everyone? Just trying to show you everything, every little step involved. So there's no problem with, there's no confusion. Now, if you take a look at that, I can get rid of the J and the negative sign. Throw it out. I've solved for C. What is C going to be? C is going to be what? Multiply both sides by C, divided by 1.1. It's going to be 1 over 2 pi times 10 to the 9, right? That's the omega. Z naught is 50, right? And then divided by 1.1. What do you get for this value of C? 2.9? 2.9. Okay, now I would have asked you to draw the circuit for the bad design. Maybe I'll ask a bad design problem, just to make sure people understand. So what does it look like if you draw it? This is my load, right here. Now we're going to draw this one. First element has to be in parallel. It's because we're in the rotated, we're in the inside the one circle, right? It's an inductor, right? Another bad design. That inductor's over there, correct? The second element is the capacitor. And then it connects to the actual transmission line right there. You all follow me? How many see this right here? Now that is all based on the condition that you're inside the one circle. We have a bad design and we have a good design. We did both. So now we're going to do another one. Can you give me one where we're in the rotated circle? I gave you a bunch. If I don't do these, I promise you on Friday, you guys are going to come here and you're going to be, huh? Because this is not that confusing, but it's hard to get people's attention sometimes on this stuff. Did you have another question? Anybody? Anybody have any other question about this particular type of problem? Where you're inside the one circle. Now I want one inside the rotated. Then we're going to do one outside of both. Those are the easy ones. So let me erase this. So any news on who the new football coach is going to be? Hey, I've heard that from so many people. I've heard Deion Sanders, Lane Kiffin, who else? Hugh Freeze. I've learned this lesson. I don't know if you know this, but you know how they say the athletic director picks the nonsense. You know who does? They hire a private firm that goes goes out there and they do a search for all the coaches, and they bring back sort of a list of coaches that will come and the price they'll come at. And then the committee, which is board members a lot of times, they figure out what's best. And then the athletic director does the rollout. If things go bad, he takes the blame and leaves. It's the way it is. I'm not kidding. I've been here a long time. I'll never forget the conversations I've had with the board. All right. So which one are we doing now? Let's do one where we're inside the rotated circle. Can you find one where if you normalize, you're inside the rotated circle? I gave you a couple. If you want me to make one up, I will, but how many did these problems, or at least took a look at them? Didn't I give you one inside the rotated? You didn't do them? Shame on you.
Yeah, this, I think 10.16.
All right.
It goes outside both.
No, not outside. Save that one. Give me the one. I think somebody texted the board. Terminated. Was that mine or somebody else's?
10.13.
Whose phone was that? Is that my phone?
10.1, yeah.
What?
10.13.
All right. That's a lousy circle, but as good as it's going to get. All right. Give me the values.
Load is 10 plus J15. Magnitude is 50 on line at 1 gigahertz.
And this is a Z naught of 50, you said?
Yes.
And F is 1 gigahertz. Okay, so here's the deal. We got something where the load is much less than the characteristic impedance, so we normalize first. When we normalize it, what do we get? 10 plus J15 over 50, right? What's that? 0.2 plus J0.3. Is that right, class? All right. Now I have to plot that. That's still impedance, though, right? You're in the impedance domain. Where's that going to be? Well, J.2 is out this way, and 0.3 is about here, so about here, and this would be 0.2 plus J0.3. Can you all see that here? This would be my ZL, normalized ZL. Find that point on that rotated Smith chart. Can you all see it? Yeah. Back there. Y'all see it? Got it back there? All right. Now, we're in the impedance domain, but look, I can add a reaction, I can add some plus J, and I can easily move here, right? Remember, that's impedance, so that's in series. Or I could move here. Y'all with me? Now, if I'm here and I add a positive impedance, positive J value, that's an inductor, right? An inductor in series, good design. Inductor in series, good design. You like that? So we're going to go from here, this is point 1, to this point 2, right here. Just follow my train of thought. Now we're on the rim. Now we go to the admittance domain. You all hear me? When I go to the admittance domain from here, I come down to here. So this will be point 3. And now I'm going to have 1 minus J something. Got me on that? Admittance, 1 minus J. So now in parallel, I'm going to add a capacitor because that's a plus J admittance. Everybody, we'll go through this carefully. Make sure you see it. So first, can somebody do this? Get on the point 2 trajectory and see where it intersects here. Just tell me what that is. Say it again. All right, so it's going to be 0.2 plus J0.4. That would be this point right there. Do you all agree? All right, the conjugate point here, if we wanted a bad design, would be 0.2 minus J0.4. There'll always be conjugate values if you're on the rim. You all with me? Hey, can you see back there behind the door? Every time I see people behind the door, I'm always concerned. They're writing, but they don't see. All right, now we're going this way first, all right? So how much do I have to add in P's? I was at what? 0.3. I need to go to 0.4. I add 0.1, J.1. So my first element, and this is going to be the design, here's my ZL. My first element is going to be just plus J0.1, and that's an impedance, a normalized impedance. now I come over here, can somebody take, 0.2 plus J.4, take one over, tell me what you get?
1 minus J2.
1 minus J2, confirm that, people? Alright, so now I need to add an admittance of plus J2. Y'all follow me? So we'll get rid of this. So the next thing is gonna be an admittance of plus J2. Remember, I'm doing this way for a very good reason. I'm trying to make sure you see all the things that can happen. These are normalized values. Alright? If you go ahead and talk amongst yourself, yeah.
So, in this case, when you're doing it inside the rotated circle, the inductor's on the right side of the capacitor.
Well,
Is that
I
on
know.
purpose?
Yes, because it's in series.
Yeah.
The only way, if you're in the impedance domain, you're adding an element, it's in series.
Yeah.
If you're in the admittance domain, you're adding an element, it's in parallel. Everybody okay with that? How many understand this, by the way? Alright, now, hear me. I don't ever like to say that. Here's why. This doesn't have to be an inductor. I could put a capacitor there if I went to the other side, right? If I didn't go up here, if I went here, that'd be a capacitor, right? It'd be a bad design, but it would be a capacitor, right? Then, coming over here, then you would add an inductor. So don't think, try to free yourself from that thought process. Always think about, if it's in series, I want to get to the rim. If it's in series, that's a reactance, right? J plus J is associated with an inductive reactance. So if I'm adding positive inductance, or positive J, then I'm adding a series inductor. If I wanted to have negative J, right, to go to that bottom point, then it would be a capacitive reactance in series. Then you always have to normalize it. Are we good on this? If you have, I'm trying to be clear. Is there something I'm not being clear about? That's the only way you need to think about this. But be very careful. Oh, the inductor's always on the right. Don't think about it. Think about in terms of fundamentally, what are you trying to accomplish? I'm trying to get to this rim, all right? If I add an inductor, I'm going this way. If I add a capacitor, I'm going that way, in series, all right? That's it. Okay, so what we're doing, we did design. So now, these are the elements, right? Now let's go ahead and get the value of the inductor. Can somebody besides the guys up front tell me? Somebody in the back there. Tell me, how do I get the value of the inductor there? Anybody? Well, then, you've been quiet all day. I'm going to start trying to stir up some trouble back there. Yeah, go ahead. This is a good way. Start with the inductive reactance. J omega L is the inductive reactance. Now we have to normalize. So we divide by Z naught, correct? So divide by Z naught. Now, what is that going to be equal to? 0.1, right? Isn't that this one? That's a series element, right? That's a series inductance, correct, class? All right, so that's 0.1, J.1. All right, so what's L? So L would be equal to 0.1, right? Times Z naught over what? Omega. All right, so 0.1. Is Z naught 50? 50, and omega is still 1 gigahertz, so it's divided by 2 pi times 10 to the 9. So go ahead. What do you get for that? You with me on this?
79.5 nanofards.
79.5 nanohenries. Nanofards. Nanohenries. Anybody else? You get it? Okay. All right. Now that checks the box for the inductor, right? Now we're going to go ahead and get the capacitor. This is an admittance in parallel. You all follow me? If it's an admittance, I know I do this and I think I irritate people, but it helps. It really does in the long run. So now I'm going to come over here, and the way I do this, I always think about the thing I know. I know capacitive reactance is 1 over J omega C. That's just the reactance of a capacitor, or the impedance. Do you agree? Then I have to normalize it, so I divide by Z naught. Now that's the normalized capacitive reactance, right? But I don't want reactance, I want normalized what? Admittance, so I take 1 over that. And 1 over that would be J omega C times Z naught, and that's equal to this. You got me on that? Right, so that's J.2, or J2, pardon. So when I look at this, I can find the value of C, and that's simply 2 over omega times Z naught. So it's 2 over 2 pi times 10 to the 9th times 50. And what do you get for that? I remember walking down one time. I was up, that was over 238. So I'm usually up there, and for some reason I came down to do something. And these kids didn't realize I came down. I'm looking at what they're doing. They're texting. They're doing fantasy football, everything but doing what they should be doing. Anyway.
6.37.
Anybody confirm that? 6.37 picofarads? You get it? Alright. Y'all follow the process on this? Alright. So help me out. Same deal, bad design this time. So now I started here, but now I'm going here, right? Remember, that's an impedance, isn't it, class? All right, so if I go from here to here, what do I add? Well, I had J.3, I want minus J.4, so I add minus J.7. You agree with that, everyone? Follow my reasoning. All right, so now this is bad design. So I'm just going to change this. So now this is a series element, but it's minus J.0.7. Agreed? You with me on this? Now I'm here. 1 over this is going to be 1 plus J2. So I'm going to end up here. And this is going to be 1 plus J2. Y'all with me? I was an impedance, that's admittance, right? Now I'm going to add something in parallel to get rid of that, which would be minus J2, right? So now this becomes minus J2. Agreed? Y'all follow me? The bad design, but it would still work at that frequency. I don't like it, but you'll find out sometimes it's good to go through both of these for a different reason altogether. And it has to do with sometimes trouble they're having where a bad design might actually reduce some of the problems. Here's why. You never put an inductor in series normally, unless there's some reason for a lot of static charge to cause an induced voltage to like build up there. Then an inductor in parallel. Then that parallel inductor will bleed off all that charge. All right, but generally speaking, it's not a good idea. Okay, now let's do this. All right, so how do I get that element? That is an impedance. It's minus J. What is a minus J impedance? Capacitors, that's right. So a capacitor has a reactance of minus J over omega C, right? But we have to normalize it or divide by Z naught. Now that is equal to the minus J right here, 0.7. You all agree with me? What value do we get for C? C would be equal to what? It would be 1 over omega Z naught 0.7. What's that value? I'm just doing this for completeness. What'd you get? You got a calculator? Anybody? Say again? 1.5. Anybody confirm that?
Yeah, I got that.
You got that? Okay. You check the box here for the series element. That's a capacitor. And I'll ask you to draw it. We'll draw it in a second. What about here? That's what? An admittance, right? So if we start with an inductive reactance, it's J omega L, right? Then we normalize, divide by Z naught. Then we take 1 over that to get the admittance. Do you all follow me? It's the normalized admittance. So this is gonna be minus J Z naught over omega L. And that is equal to minus J2, isn't it? But the reason I'm doing it this way, always think of the things you know best. You know the impedance of these elements. Start there, then normalize the impedance, then flip it to get the admittance. I promise you, you'll thank me for that, because people mess that up all the time. They try to think, oh, the Z naught doesn't go here or here. And they don't understand how easy it is if you just remember why we're doing it. Okay, so this is equal to this, or minus J2, so what is L? Just look at that. L would be equal to what? Multiply by L, divide by 2. Z naught, right? And it's over 2 omega naught, and that's 2 pi times 10 to the 9. So what do you get for Z naught is 50.
3.98 nanometers.
Anybody confirm? Good design, bad design. Hopefully you guys get it. Now we're going to do one in the time remaining that's outside both. There's 4 possible ways to do those designs. On these, there's only 2. If they're inside the rotator or inside the one circle, there's only 2 ways, 2 possibilities for a capacitor inductor battery. When you're outside of both, there are 4. And you got a lot of options. It's like whatever you feel good with, go with. But generally speaking, inductors in series, capacitors in parallel. Okay. So let me get the next one. All right. All right, so which one was outside of them? I know I did. All right, give me it.
Says, you want to match a 20 plus J 50 ohm load to a 50 ohm line.
Z naught is 50? This is crazy. Okay.
Says, for the design of an L section matching network, you notice an normalized load unit side on side both to one circle in the rotated circle. Find all 4 possible solutions.
Yeah, this is a whimper from.
And for each one, determine the values of the lump element at 2.5 gigahertz operating.
Alright, we'll get to that frequency in a second. Now I want you to think about this rationally. All right? First, we got to normalize and plot it, right? So when we normalize this and plot it, what do you get? We got 20 plus J50 over 50, so we got what? 0.4 plus J1, correct? Now I got to find that. So if I look at that, the J1 is right up here. Right? The 0.4, this is one circle. The 0.4 circle is probably about like that. So that means if I look at this, it's going to be here would be my first point, which would be 0.4 plus J0 or plus J1. Y'all follow me? I want you to listen. That's impedance, right? Now, we can add or subtract impedance. No matter what I do, I can never get to the rim of this circle by moving along this path. It will never intersect. Y'all follow me? Only way I can get to the circle is move to this one. And I got 2 possibilities. I can add something to series impedance and I can get to this point. Y'all agree with that? That would be what? If that's J.1, I would be adding a negative J to get over here, wouldn't I, class? Y'all follow me? Because this is J0, this is like J0.25, stuff like this. And these are trajectories. So I start at 1, if I subtract something, it would be a capacitor, I move to there. Do you agree with that? Alright, now that would be this point. I could keep on adding, right, or subtracting, in this case, J, get a bigger capacitor, and I can move here too. You all follow? You would still have a real value of 0.4. but it would be at here or here, correct? Now that's adding two different elements in series, the possibility that if I land here, alright, if I add a capacitor reactance in series, so I land here, then when I go to the conjugate point, I'd be in the admittance domain, I'd have 1 minus J something admittance, correct? I have to add a plus J, right, which would be capacitor, right? So you would have two capacitors. Do you all hear me on this? Now just listen to me, right? Add a bigger capacitor, or basically take off more J, get it down to here. Now if I'm at this point, right, when I come over here, I'm going to have 1 plus J something. Do you all hear me? In the admittance domain, right? So that would be an inductor, right? Because the admittance of an inductor is minus J. You all hear me? So now I've got two design possibilities, moving that way with the series element first. Does everybody follow me on that? Now what if we don't put a series element? Let's go right to the admittance domain. Then I take 1 over that, and I come down here. That was ZL, this would be what? YL, right? Now what do I want to do? If I'm over here, I got possibilities. I want to move to here, right? That would be adding a positive J something. You all follow me? This is going to be 1 minus J, it's not 1, it's going to be, there's a minus J here, all right? I'm going to add something to get to the rim. I could go to here, and remember this is admittance, or I could keep going and go to here, right? Can go to two possible points. Do y'all follow me? Then when I'm at either of these points, now I'm in the admittance domain, when I go back over here, I'm in the impedance domain. So if I move to this point, still adding a capacitor, or excuse me, admittance, I'd be adding an inductor. Now, if I move from here to here, I've got 1 plus J. I was admittance, now I'm impedance. That means I'd add a capacitor, minus J, right? Correct, class? And if I moved up here, and it was minus J, right? Do y'all follow me? In admittance? I'm sorry, it'd be 1 plus J something up here, then I would add a minus J in the impedance domain. Sorry. We're going to do a few of these, but I'm talking my way into some problems. I'm trying to run through them. I'm already out of time. Let's do at least one of them. How about we do this one? We start there. Help me out, guys. And get me to this point. Tell me what this point is. 0.4 plus J what? Plus J what? 0.5. Anybody confirm that? All right, that's an impedance. So we started at 1, went down to 0.5, we added a minus J.5. Is that right? You agree? So now I know I have an impedance of minus J0.5 right here. Now I'm here. Now take 0.4 plus J.5 and 1 over it. Is this the 1 plus J, the 1 minus J2? What do you get for that one? .4 plus J.5? 1 minus what?
1.2 J.
Minus J 1.2? So this is 1 minus J 1.2, is that what you said? Is that it? Alright. This is impedance. Now we're in admittance, right? Now we have to add a plus J 1.2, which is here. Okay. Briefly, I know I'm out of time, but work with me. That's impedance, right? What has a minus J impedance? Capacitor, right? Y'all agree? So now I say minus J 0.5 is equal to the capacitor reactance, which is minus J over omega C divided by Z naught. That would be the value, and this is how we get C. And I know F is 2.5 gigahertz, so omega is different for this one. But you all follow me? I want to make sure. I know. Now, we'll get that in a second. What about this? That's an admittance, right? That'll be a capacitor. So you're going to take capacitive reactance as 1 over J omega C, normalize it, it's 1 over J omega C Z naught, flip that, and you got the normalized admittance. So that means for that one we have J 1.2 is equal to J, and this is gonna be, omega C Z naught, correct? Sorry, what? All right, you all agree with that? All right, now you can figure out with C and, this, yeah, you can figure out with C is there and C is there. Do you agree with that, class? This is just straightforward calculations. Please go through these. But the nice thing about when it's outside either one of these, I can do series impedance first, and I have two possibilities, or I can just flip it and go into the admittance domain right away and add parallel admittance. Okay, see you on Friday, you're getting a quiz related to this. I don't know why I'm so silly, listening to all this stuff on the radio, but to the next cover shoes. I heard some whoppers too, man. Lane Kiffin's gonna go to Alabama. Really? There's a guy up there now, it's not doing too bad.